Okay, last week we have already introduced some critical vector operation principles, including the dot product and cross product. They are referred to as 内积 and 外积 in memory. And here are here is an operation associated with the cross product. It's referred to as the triple cross product. So as you can see, the triple cross product is performed by taking cross product on 3 vectors, and 2 of them will do first, and then cross product with the result will be cross product with another vector after that. And note that the order of triple cross product is critical because if you're taking A cross B cross C, and if you do B cross C first, and on the other hand, if you do A cross B first, that will be different. And for the cross product, if there is no parenthesis, 没有这个括弧的符号的话，the order will be A cross B first, then the result of A cross B shall be cross product with vector C. Of course, if the parentheses are lower, and you should follow the order according to the parentheses. All right. So, for example, if vector A is A1, B is A1 as well, and C is A2. Then if you take B cross C first, A1 cross A2 will end up with A3, then you will have A1 cross A3, and you get minus A2. On the other hand, if you do A cross B first, because the 2 vectors are the same, so the cross product result is 0, and then you end up with 0 vector. Another 3-vector product that is used very frequently is the so-called scalar triple product. So note that the expression for the scalar triple product for this example is A dot B cross C, and the priority of cross product is higher than dot product. So you should do cross product first, even though there is no parenthesis on this expression. So without the parenthesis, you do cross product first, so you get B cross C first. Then you do the scalar product, that is the dot product of A dot result of B cross C. So what is the end product of this scalar triple product? Well, it's a scalar or a vector? It's a scalar, because the later operation on this expression is the dot product. So you end up with a scalar, okay? So the scalar triple product can be performed or can be conducted using the determinant form fashion, like what we have in 1.21. So you write up the projection of vector A1, A2, and vector A, B, and C on the 3 rows of the determinant form, and you can use the determinant form fashion to find out the result. Now that will be A1 times B2 times C3 minus A1 times B3 times C2 plus A2 times B3 times C1 minus A2 times B1 times C3, so on and so forth. So that will eventually give you a number, a scalar, for the result of a scalar triple product. Another property associated with the scalar triple product is so-called the cylindrical manner. Not cylindrical manner, 讲错了 cyclic manner 轮转的特性也就是说 A 打 B cross C 等于 B 打 C cross A 等于 C 打 A cross B 所以这是向量运作的一些小技巧那 虽然说看起来它没有直接的跟电磁学的关系哈，但是我们后面在一些电磁的一些关系哈，一些电磁理论的一些重要关系式的推导里头会用到这一个轮转的特性哈 ，cyclic manner 哈，像那种 scalar triple product 的这个 cyclic manner， 所以还是稍微看一下哈，了解有这样的特性存在哈。So the result is the determinant form remains unchanged if the rows are interchanged in a cyclic manner. So the result A dot B. So you can move the first row A into the second row, and if you move second row B to the third row and the third row back to the first row, then the result is the same. So A dot B cross C equals to B dot C cross A. So you can verify that yourself. Then we will show some other features associated with scalar triple product. Now, in this slide, we show that the distributive law still holds for the scalar triple product. But not for the cross product, sorry. So A cross B plus C is the same as A cross B plus A cross C. So this is the original expression, and we would like to show that this relationship holds by using the cyclic manner that we have seen in the previous slide. So suppose that we have an arbitrary vector D, and you do D, you perform scalar triple product on this result. So this is a simple two-vector cross product, A cross B plus C. But A cross B plus C, according to the cyclic manner, is the same as B plus C. You move this one to the first and move this one to the second position, and A to the third position like this. So you have B plus C dot D cross A, and we know that a distributive law holds for dot product. So you can separate the expression here into two scalar triple product, B dot D cross A plus C dot D cross A. And use the cyclic manner again, that you can move D to the first position. And you have you can show that D is this this can be this is the same as D dot A cross B and D dot A cross C, and then you use the distributive product for dot product again. You can collect the two terms in the back as A cross B plus A cross C dot D, so that you kind of prove or kind of show that the distributive property, distributive law, is also holds for cross product. All right. So to place with this equations when you review the course content at home. All right. All right. So next, let's move on to the introduction of coordinate system. Because in electromagnetics, we are dealing fields and waves that is propagating or existing in actual environment, that is a 3D environment. So the spatial property, spatial 是空间的嘛哈 the spatial property should be described using a three-dimensional coordinate system. Of course, you are familiar with the so-called rectangular coordinate system, which is referred to as the Cartesian coordinate system in the textbook. However, in section 1.3, we are introduce another two coordinate system type, that is the cylindrical coordinate system, 圆柱坐标系统, and the spherical coordinate system, 球坐标系统, which are In some cases, or well, in most cases, the spherical coordinate system is more suitable for describing wave propagation in space. All right. So here is an illustration of the Cartesian coordinate system. So what is the first thing you should not notice from here? Well, what is the reference direction? 参考坐标方向 X, Y, Z 嘛，对不对？So you see here is the AX, AY, and AC, the three unit vector for the reference direction. So Cartesian coordinate system in general or in principle is described in terms of AX, AY, and AZ. And note that there are three planes drawn in this figure. What are they? They are the plane, a two-dimensional plane, spanned by two of the reference direction. 所以两个参考方向可以张出一个平面。所以在这个直角坐标系统里头，你有看到水平的 XY 平面、立起来的 XZ 平面，还有另外一个 YZ 平面。What are the geometric relationship between the reference direction and the planes expanded by two of the three reference direction? Well, first thing you should notice that the reference direction are perpendicular to each other. They are orthogonal to each other. They are 垂直嘛，互相的垂直。它们的平面也是互相，它们所张开来的平面也是互相垂直嘛。So you also know that the plane expanded by the reference direction, the XZ, YZ, and XY planes are orthogonal to each other at any place in the coordinate system. Okay? In any place in the coordinate system. Suppose that in this classroom, I define the x direction is over here. It's pointing towards this direction. Y direction is over here. What is the z direction? Well, it can be found by taking the right-hand square rule. So z direction is pointing upward. Okay? So according to my direction, that is x direction over there, y direction over there, z direction over towards this place, what is the x direction at your position? 那边嘛，对不对？我已经定义了，说 x 方向对不对 ？y 方向对 z 方向。请问你坐的那个地方，你屁股坐的地方，你的 x 方向在哪边？不是吗 ？z y 方向嘞？好 ，OK。是早上的关系吗？大家看起来有点茫然了。OK， 好。所以这个东西告诉我们什么事情？在直角坐标系统里头有一个重要的特性叫做 uniform。The direction is uniform in the Cartesian coordinate system. That is, the x direction, my x and my ax direction is in fact in parallel with the ax direction of the opposition. 你的 x 方向跟我的 x 方向其实是互相平行的，我的 z 方向跟你的 z 方向一样都是朝着上面的，所以这个性质叫做 uniform 一致性。而这个一致性的特性，其实只有在直角坐标系统里头存在。所以要珍惜这个特性在直角坐标系统里头有一个好用的特性和方便的特性，就是说它的方向都是具有一致性的。而这个一致性的特性，在我们接下来要提的柱坐标系统和球坐标系统里头不是这样要小心Alright, so here we can notice that the uniform property is holds for the Cartesian coordinate system. As already mentioned in 3D space, to define a coordinate system, you require three reference directions, and they are orthogonal to each other. And down below you see that the three coordinate systems that we will look into are Cartesian, cylindrical, and spherical, which are useful in different scenarios. And so here we see the Cartesian coordinate system is defined by a set of mutually orthogonal planes 三个正交的平面，互为正交的平面，而这三个参法方向 x, y, and z are perpendicular to each other, not perpendicular to each other. And the so-called unit vector, 3 reference unit vector are labeled as AX, AY, and AZ. And as I already mentioned last week, the 3 reference directions are by the so-called right-hand square rule. So the order x, y, z also determines that if you take in the cross product of ax and ay, you will end up with positive az direction. On the other hand, if you do the cross product reversely, that ay cross ax, you will end up with minus az direction. So the sign should be followed, the positive or negative sign should be followed by the right-handed system, right-hand square rule, all right? And as I already mentioned, in the Cartesian coordinate system, a very important and convenient property about the 3 reference direction is they are pointing toward the same direction at all positions, at all locations. So this behavior is not, however, does not hold for other coordinate systems such as the cylindrical and spherical coordinate system, all right? And it's only holds for Cartesian coordinate system. Next, let's look at some operation example for coordinate system. So I believe this is should be straightforward for you guys. So suppose we have a vector named as R12. Be careful about the order, about the subscript. 所以在看向量的时候，它的那个下标的顺序是有意义的哦。所以这边你看到这个向量 R， 它写作什么 R subscript 12， 意思指的什么？它从这个向量是从 point 1指向 point 2， 可以吗？稍微记一下这一个规则啊。So R12 is a vector pointing from position 1 to position 2. It can be written as R2 minus R1. What R1 and R2 are? Well, R1 is the vector starting from the origin and ends at position 1, while R2 is another vector starting from the origin and ends up at position 2. So if you draw the 3 vectors on in a 3-dimensional space, you see that here's point 1, and here's point 2. R2 starts from O, from the origin of the Cartesian coordinate system, and ends up at point 2. R1 is this vector from O to P1. Then R12, which is, as the figure shows, is a vector starting from P1 to P2, can be expressed as R2 minus R1, R2 minus R1. Why? Because R12 can be think of as the difference between point 1 and point 2 according to their projections on x, y, and z axis. So as the equation shows, the x component of R12 is x2 minus x1. That is, the projection of R2 on x direction minus the projection of R1, which is x1 over there. And the difference is the movement of the vector along the x direction. And so the similar fashion can be followed for the projection on y and z direction. Right? 好吧，所以这个图要去看一下，理解一下哈。也就是说 ，R12 这个向量哈，它是 point1 跟 point2 这两个点在直角坐标系统里头3个分量的投影量的相减，那刚好会是等于 R2 减 R1 这两个从原点出发的向量的相减结果。Right? So R12, which describes the vector starting from point 1 to point 2, is of course a vector. So when you write up the vector, do use this form. Okay? Write the x component, y component, and z component with summation signs. 好，再警告一次哦，考试的时候你不这样写的话，就是杠掉了，好不好？你要是给我写成一个括弧，然后写5、6、7我就看着就不爽 ，OK？ 好，我已经讲过了，请你这样写 ，Alright？ So that's the formal expression for describing a vector that I urge you to recognize this. And down below is the calculation for the unit vector for R12. So the unit vector should be written as A, that is a parameter denoted to the description of unit vector. 1, 2 can be found as the vector R12 itself divided by the magnitude of R12, like this. So because it divides the magnitude of itself, so I can write this way or this way, just express not the difference between the denominator and numerator. 分子跟分母差在哪里？上礼拜讲没来上课的话，假如上礼拜没有 pay attention 的话，这两个差在哪里？上面的向量，下面是存量啊，对不对？所以上面是大小加方向，下面只有大小，所以你把这样相除的话，把大小除掉了所以剩下的就是单纯方向的描述。然后从数值的运算的话，就像右边的So in the denominator you have vector expression that is x2 minus x1 in the direction of ax, y2 minus y1 in the direction of ay, and in the denominator is the square sum, the square root of the square sum of the projection of the vector on the 3 reference direction, like this. Alright, so in our study of electromagnetic fields, we have to work with line integral, surface integral, and volume integral. I mean, so far, the operation of vectors, the idea of coordinate system are, I believe, you are already acquainted with that. And the idea of line integral, surface integral, and volume integral, I believe you have also seen that, so that in your freshman year calculus or engineering mathematics, but unfortunately you probably do not have many chances to use that. Unfortunately, in this course, we will need to work on the idea of differentials as well as integral. To perform integral, you need to be aware of the idea of differentials, right? And differentials are described as to perform line integral, surface integral, and volume integral, 线积分、面积分、体积分, you should be aware of the idea of differential length, differential surface, and differential volume. 线的差分、面的差分，还有体差分。所以我们 要执行积分之前，我们要在式子里头写出差分的概念，而这个差分包含线的差分、面的差分，还有体积的差分。OK， 所以在 1.2 里头，我们的重点其实是落在这几个概念line differential length, differential surface, and differential volume. All right. In Cartesian coordinate system, we know the three coordinates represent lengths. So the differential length elements can be obtained by increment one coordinate at a time and keeping the other two coordinate constant. So the small increment in the x direction is referred to as dx/ax. So dx represents a small amount of increase in the x direction. Is that a scalar or a vector? Well, it's a scalar. No, it's only a description of a small amount. But if it follows with ax, then it becomes a vector. It describes that along the x direction, you have observed a small amount of increase in the x coordinate, in the x-axis, 在 x 轴上面有一个小小的增加。那同样的这一个小小的增加也可以被描述在 y 跟 z 方向。So you follow the same some similar fashion. You can write up a small increase in the y and z direction, dz/az, accordingly. And this expression is referred to as dl. That is differential length. (有纸笔的现在写个3遍没有纸笔的念个3遍，把它给背起来。Differential length 因为第一章里头一个重要的概念，然后会被用到第2章的，就是 differential length。Well, so of course the differential length is a general description. It just describes that an arbitrary piece of length, very small, position in what coordinate system? Cartesian coordinate system. So what is the exact length of this? Well, the length of dl should be computed as what? The square root of the square sine of dx, dy, and dz, right? Dx to the square plus dy to the square plus dz to the square, and taking the square root of that. But it's a general description. So it can be any vector, any short pieces of length residing in the Cartesian coordinate system. And dx, dy, and dz are the projection of dl on x, y, and z direction. And important thing to note is that the projection, dx, dy, and dz, as well as the dl, have certain lengths, 是有长度的even though in the expression there, you don't know what exactly the length of that, but you know it's a small one, all right? So this definition is convenient for taking out the so-called line integral. So if you want to perform line integral, 线积分, you should begin with differential length vector. So as I already write on the blackboard, dl equals to dx/ax plus dy/ay plus dz/az is the general expression for differential length in Cartesian coordinate system. This is a vector, scalar vector, scalar vector, scalar vector. So in the study of electromagnetics, you are encouraged or you are recommended to do translation, in particular translation between mathematical expression and 中文或英文 as you prefer. 我们试着把课本上面的式子去做一个翻译，好不好？你要试着去练习，把式子用你能够理解的中文或者是你可以理解的英文来去把它翻译出来。所以像这一个我们讲 differential lens 差分向量的概念就可以被理解成什么？当然这是我的翻译啦哈。我认为在空间的一个小幅度的变动量，就是你这个线差分的描述，可以被视为是 x 方向上面的小变动量加上 y 方向的小变动量加上 z 方向的小变动量，好不好？你把这个翻译记起来、理解起来，那你再把它换成数学式的表示上面，应该就会比较容易一点、舒服一点吧？OK， 好。再一次啊哈，电磁以为你的数学不难啊，它就比较烦而已同样的事情要做3次啊，因为在三维空间嘛，对不对？OK， 不难啊，就是烦一点。Alright, so in this slide we see there are 2 points, point P and point Q. Point P is labeled as P as that's position P. We label with its coordinates x, y, z. And another point, position Q, which has slightly different coordinates with respect to point P. So it's written as x plus dx, y plus dy, and z plus dz. So you have some difference between the coordinates of the 2 points. And then the differential length dl describe the vector starting from P to Q, then the projection of dl on the 3 coordinates shall be dx, dy, and dz. So that's the principal idea of differential length. The differential lenses dx, dy, and dz are not independent of each other if they are used to describe in the same differential length. In the description of differential length 线差分向量的描述里头，它的 x 分量跟 y 分量跟 z 分量不是独立的而是被 bound 在一起。为什么？因为它们被拿来去描述一个向量，描述这个线差分向量。所以意思是说，当你的 dx 方向上面的变动量 dx有一点改变的时候，你沿着这个 dx 变动，然后你就要遵照 dl 这一个向量的描述去给它相同比例的 dy 的变化，相同比例的 z 方向的上面的变化，也就是 dz 的变化，也就是 dx、dy 跟 dz 这3个在 reference direction 上面的投影量是有 dependence， 是有一个比例的假如说你用一个 differential length 把这3个方向的投影量bound在一起来去形容这个 dl 的时候所以这样的结果就由 example 1.2 来去展示说它的效用了So we will use example 1.2 to show the relationship between the projection of the differential length on the 3 reference direction to show the relationship. So let's consider a curve which is x equals to y equals to z to the square. Can you imagine what is this? S equals to y equals to z to the square. Well, it's actually a curve, parabolic curve in a 3-dimensional space. 所以这个 x 等于 y 等于 z 的平方，它是一个抛物线的描述在资料坐标系统里头OK， 所以右下角那个图可以让你看得出来，它 x 等于 y 等于 z 平方其实是一条线，一条弧线，一条抛物线所以那你看一下为什么我们说 x 等于 y 等于 z 的平方是一条抛物线Because well, of course, every point stays within this line should abide the relationship between the 3 coordinates. Between the 3 coordinates labeled, that is x equal to y equals to z to the square. For example, if x equal to 1, what is y? 1. What is, well, we have 2 options, +1 or -1, right? So if x and y is 1, then there will be 2 points can be described, can stay on this line. That will be 1, 1, 1 over here, and 1, 1 minus 1 down there, right? So actually, if you have x equals to 1, y equals to 1, you have 2 options, 2 solutions for z. That will be positive 1 and negative 1, right? And you can you can find out other points on this line in a similar fashion. So for example, if x equals to 2, y equals to what is z? Square root of 2, positive and negative, right? Now, all right, so next, so this is the general expression for the differential length. Keep in mind that you will use this expression all the time when you come up with this kind of problem. And what you need to do is perform differentiation on the description of the line. So here you have x equals to y equals to z to the square. What do I mean? Taking the differential of that. So originally you have s equals to y equals to z to the square. If you do the differentiation, well, first, nothing to, you have dx equals to dy equals to 2 times z times dz, all right? So you just do the differentiation on the 3 components, So we end up with a general expression for the differentiation of the description of the line. So on the blackboard, I write up dx equals dy equals 2 times z times dz. So it means one portion of change in the x direction is proportional to one portion of change in the y direction. However, one portion of change in the x direction is proportional to 2 times dz times the coordinate description about z. 所以在这个式子里头，你看到的物理意义是什么？这一条线告诉你的是，你 x 方向每变动1分，不管是增加或减少，它会对应到1份的 y 方向上面的变动，可以吧？这样的变动其实叫做什么？线性的变动 ，proportional。但是当你在谈 x 跟 z 方向上面的变动的时候，这边看出来什么？1份的 x 方向的变动等于它所对应的那个位置的 z 坐标2倍的 z 坐标乘上底 z， 所以它不但对应到 z 的那个变动量，它也对应到 z 的坐标位置。小心要小心的是这边写出来的说，你的 dx 跟 dz 的变动量是跟你的坐标是有关的。前面的半段没有告诉你说 x 跟 y 的变动跟坐标其实没关系，但是后面这个的话呢，因为有这个 z 的存在，所以它跟坐标位置是有关系的，跟坐标位置是有关系的，这是要小心的。所以在这个例子里头，我们检测的位置是哪里？111这个点So suppose we are looking at the point 111. Then when you want to find out the relationship between dx, dy, and dz, you need to substitute the description of the coordinates. For this example, that will be z equals to 1. So this thing ends up as 2 times dz equals to 2 dx, dy, at this position, 1, 1, 1. On the other hand, if you are looking at the position 4, 4, 2, then what is the relationship between dx, dy, and dz at 4, 4, 2? Well, you still begin with dx equals to dy. However, because z is what? 2 over here. So it will be 4 times dz at 4, 4, 2. That's the reason why when you look at the parabolic curve, parabolic line, you found that the difference, the change in the z direction becomes less as it moves away from the origin. 所以你会看到 那个抛物线的那个斜率当 x 跟 y 的坐标变大的时候，它在 z 方向的变化量就越来越小，所以它开始躺平开始躺平斜率变小。那原因什么？原因是它的这个地方的 differential length 跟这个地方的 differential length 不一样。所以另外一个从物理的观点去看 differential length 的描述是什么 ？differential length 描述的现在这是一条线嘛，所以 differential length 告诉你的是这一条线的斜率，或者说它的 tangential 的方向tangential 切分方向嘛所以在这条线上面的切分方向，所以你去算它的 differential length， 其实就算这一个点的切分方向。所以这个点的切分方向跟111的切分方向跟442的切分方向也不一样OK， 不太一样他们的那个线差分向量，他们的切分方向，他们的 DL 是不一样的So the differential length is a function of the position as well as the function of the description of the line itself. So they are different. So you should be aware of that difference. Okay? And differential length vectors are useful for finding the unit vector normal to a surface at a point on the surface. As we have already mentioned, if you take in the cross product of two vectors, you will end up with a new vector that is perpendicular to the two vectors originally. So you can imagine that the cross product of any two vectors forms or expands a so-called surface. So in this slide, in this figure, you have A cross B, which can be two arbitrary vectors reside in the space. And the cross product will be a new vector that is perpendicular or orthogonal to the two original vectors. So it is referred to as the normal vector, 法线方向，法线向量。So equation 1.20 shows you the definition of the normal vector, which is a unit vector pointing to the normal direction of the surface expanded by vector A and vector B. So that would be A cross B divided by the absolute value of A cross B. In other words, you can write up a more general expression for 1.28. So AN equals to DL1 cross DL2 divided by the absolute value of DL1 cross DL2. So any two differential lengths can expand a small region. And small surface, small region is described by its normal vector. So this is kind of this equation is kind of the idea of differential surface. 我们刚刚讲的线差分嘛，我们刚刚讲的介绍是线差分向量。我们接下来讲的是面差分向量 differential surface 所以你要想看在空间中的一个小小的面，你要怎么描述它？面积吗？因为它有面积嘛，但我们讲的小小的嘛，所以它的描述是什么？ds ds 指的是这一个面 surface 的量，但是空间中的一个面可以朝这边，可以朝那边，你要怎么描述它？你要就变成用 as 了，你用一个向量描述这一个面的法线方向，这样你就可以定义空间中任意的一个小小的面由它的法线方向 as 所以 as 指的是 ds 这一个面它的法线方向但聪明的同学可能会有一个疑问假如说这个是空间中的一个面请问它的面的方向在哪里？那我说这里可不可以？也是啊所以事实上面方向其实有两个但那这当然会在定义上面造成一个问题啦所以不过还好啦，在电磁学里的我们后来会发现大部分你要处理的面是，假如是开放面像我刚刚讲的那个开放面，那当然一个面有 正反两个方向。但是假如说像这一个是我们说它一个封闭面嘛 ，closed surface， 那么它的面方向 by definition is the direction pointing out， 朝外的方向啊，定义为这个封闭面的方向。OK， 好。Alright, okay. Let's talk about example 1.3. Okay, so in this example, you are asked to find the unit vector normal to the surface of 2x to the square plus y to the square equals to 6 at the point 1, 2, and 6, 1, 2, 0. So what is 2x to the square and y square equals to what kind of a surface it is? Well, it's not a 我这边写的是柱面嘛，哈，其实不太正确，它是一个什么椭圆柱面 ，ellipsoid， 有点不记得，柱面是 cylinder 啦，椭圆呢，我记得椭圆面好像是 ellipsoid， 对吧？反正也是一个圆柱面了，但是它是椭圆形的吧？哦 ，OK， so this surface is well, the axis of the surface is in parallel with the z direction. And its projection on the xy plane equals to 2x to the square plus y to the square equals to 6. So in fact, if you are not consider the change in the z direction, you will have a ellipse on the xy plane, right? So the problem asks you to find out the normal direction, the unit vector normal to the surface at a position 1, 2, and 0. So the position 1, 2, and 0 is critical because if you change the position, you will end up with different answers. So the answer is dependent of the position. So for this example, the first thing is write up the two differential lengths as the figure shows. If you can find out two differential lengths, DL1 and DL2, that is reside on the surface, in particular reside at the position 1, 2, 0. Then you can do the cross product of DL1 cross DL2 to end up with the normal direction of the surface. Unfortunately, we are running out of time, so I'll probably start here and continue with this example tomorrow. All right.